Good day to everyone. We are the Group 8. Today, we will present to you the different magnetic fields. Now, I'll just review what Group 7 did with their Faraday's law. But I'll go with Lenz's law. Lenz's law of electromagnetic induction states that the direction of current induced in a conductor by a changing magnetic field is such that the magnetic field created by the induced current opposes the initial changing magnetic field which was produced. For our example, as you can see, when the North Pole magnet is approaching towards the North Pole of the coil, the magnetic flux linking to the pole is increasing. In Faraday's law of electromagnetic induction, if there is a charge in flux, an electromagnetic force, and hence the current is induced in the coil, and this will create its own magnetic field, as said earlier. Now, in Lenz's law, the magnetic field created will oppose its own or opposes the increase in flux through coil, and this is possible only if approaching coil side attains north polarity and north polarity of the coil, because we know similar poles repels each other, and after that we can easily determine the direction of the induced current. But when the north polarity of magnet and the south polarity of the coil, it will have a negative magnetic charge or magnetic field because it doesn't repel each other. The Lenz's law formula is induced EMF equals negative N, or the number of turns in coil or the number of loops, times the change in magnetic flux divided by the time that is represented by seconds. Lenz's law is based on Faraday's law, as what I said. Faraday's law tells us that a changing magnetic field will induce a current in a conductor, while Lenz's law tells us that the direction of this induced current which opposes the initial changing magnetic field which was produced earlier. This is signified as the formula of Faraday's law by a negative sign before the number of turns of coil. In Lenz's law states when an EMF or electromotive force is generated by a change in magnetic flux, the polarity of induced EMF that is produces in induced current whose magnetic field opposes the initial changing magnetic field will be produced again. The negative sign used in Faraday's law of induction indicates that the induced EMF and the change in magnetic flux have opposite signs. Now let's describe the direction of the induced electric field, magnetic field, and the current of a conducting and non-conducting loop using Lenz's law. As I say earlier, Lenz's law indicates the direction of the induced current. And because like magnetic poles repel each other, Lenz's law states that when the north pole of the bar and the magnet of the coil is approaching, the induced current flows in such a way as to make the side of the coil nearest to the pole of the bar magnet itself of the north pole to oppose the approaching bar magnet. Next on, let's compare and contrast alternating current and direct current, or AC and DC. AC, or alternating current, is a type of electrical current in which the direction of the flow of electrons switches back and forth at the regular intervals or cycles. The current flowing in power lines and normal household electricity that comes from a wall or wall outlet is alternating current. While DC, or direct current, is an electrical current which flows consistently in one direction. The current that flows in a flashlight or another appliances running on batteries is direct current. As you can see in the example, direct current has a green line which flows consistently in one direction, while alternating current has a flows direction. Now let's characterize the properties that store energy and time and currents and voltages of an LC circuit. LC circuit is a type of an electric circuit that is made up of an inductor, which is expressed by the letter L, and the capacitor represented by the letter C. Here, both are connected in a single circuit. An LC circuit is also sometimes referred to as a tank circuit, a resonant circuit, or tuned circuit. An LC circuit acts as a major component in various electronic devices like radio equipment or circuit like filters, oscillators, and tuners. For the application or uses of LC circuit, we have this signal processing. LC circuits are utilized either to pick out or generate a signal at a certain frequency. It also turning radio transmitters and receivers at the most common application of tank circuits. For instance, when you tune a radio to some station, the LC circuit set a resonance for the carrier frequency. Now let's proceed to the Malus law of polarization. Louis Malus is born in 23 of 1775 in Paris. He is a French physicist who discovered the light, when reflected and becomes a partially plane polarized. Its rays vibrate in the same plane, and his observation led to a better understanding of propagation of light. Malus' law states that the intensity of the plane polarized light that passes through an analyzer varies as the square of the cosine of the angle between the plane of the polarizer and the transmission axis of the analyzer. The polarizer is a plane of vibration of an electromagnetic light. As you can see in the example, we have the unpolarized light, we have the different direction of lights, and it travels through a direction of transmission plane of polarizer. And it passes also through an analyzer, which is a kind also of a polarizer, and have a direction of transmission of a plane of polarizer too. And we have this angle here that it is a angle between polarizer and analyzer's plane of transition or transmission rather. Now in Malus' formula, we have 2 points. In point 1, when unpolarized light is incident on an ideal polarizer, the intensity of the transmitted light is exactly half that of the incident unpolarized light, no matter how the polarizing axis is oriented. In point 2, an ideal polarizing filter passes 100% of incident of unpolarized light that is polarized to the direction of filters. And now we can assume that we have the point 1 and point 2, and we have this kind of formula, I/O times cosine squared. This is one example of Malus' law of polarization.
For today's topic, we're going to discuss the Maxwell's synthesis of electricity, magnetism, and optics, and also the M waves and light. Electromagnetic waves are members of a family of waves with common properties called the electromagnetic spectrum. While Maxwell was developing his all-encompassing equations, he predicted the existence of electromagnetic waves, which are the waves that allow you to see your surroundings and communicate with friends 1,000 miles away. When James Maxwell assembled his dream team of electromagnetic equations, he began with ideas and mathematics established by other physicists, but he combined them to create a new complete understanding of electromagnetism. Maxwell's first equation is a variation on Gauss's law, which states that the electric flux through a closed surface is proportional to the total charge enclosed by the surface. A closed surface in this case is just a surface of any shape that completely encloses a charge, like a sphere or any other three-dimensional shape. And electric flux is a measurement of the electric field that passes through a specific area. According to this equation, the electric flux is the integral of the electric field over the surface, which is equal to enclosed charge divided by the permittivity of free space. The permittivity of free space is a constant of proportionality we've used before. that relates electric charge to the physical effect of electric fields. If the electric field is constant over the surface, then the left side of the equation becomes E times A. Next, Maxwell's second equation is also a form of Gauss's law, only the magnetic flux instead of electric flux. Magnetic sources are always dipoles with a north-south pole and magnetic field lines that leave from the north pole and return back to the south. This results in the overall magnetic flux being zero. If you compare this with Maxwell's first equation, you can tell that the format with the integral of the magnetic field over the surface area is the same, but the integral will always equal zero for a closed surface. Maxwell's third equation doesn't have anything to do with Gauss's law, instead it's Faraday's law. Faraday's law of induction says that the changing magnetic field will induce an electromotive force in a loop of wire. Maxwell's version is more general, simplifying Faraday's law to show the value of that induced EMF. It says that the EMF is equal to the line integral of the electric field over a closed loop. With this equation, you can see the connection between a changing magnetic flux and an induced electric field. And the final equation is one that Maxwell made the most tweaks to in order to make it applicable to all the electromagnetic phenomena. After all, if a changing magnetic flux produces an electric field, why is there not a complementary law saying the reverse? Why couldn't change electric flux result in an induced magnetic field? Maxwell started with Ampere's law, which states that a current through wire includes a magnetic field around the path surrounding the wire, in order to make this equation full for all possible electromagnetic scenarios. Maxwell needed to consider a situation where a magnetic field is induced but not from the flow current. For example, picture a charged capacitor that is connected to wires on both sides. As the capacitor discharges, current runs through both wires, generating changing magnetic flux just like Ampere's law says. In order to account for the magnetic flux generated by this wireless current, Maxwell added what is known as the displacement current into Ampere's law to complete the equation. Mathematically, the displacement current is equal to the change in the capacitor's charge over time, and that is equal to the change electric flux over time, multiplied by the permittivity of free space constant. With the addition he made to Ampere's law, Maxwell's equations were complete, and using his laws today, we can see a pattern in the production of electric and magnetic fields. These oscillations are electromagnetic waves, and they are made up of changing electric fields that travel through space. Maxwell believed that we could reproduce electromagnetic waves in the laboratory, and he was right. To prove it, let us look at an object that can produce electromagnetic waves and transmit them through the air: an antenna. This antenna is made up of two conductive rods, each attached to opposite ends of an AC generator. When the antenna is operating, the two rods switch between being positively charged and negatively charged.
Are you ready for this? Since I love them.
As the generator charge voltage, and when one rod is positively charged, the other negatively charged, and vice versa. The electric fields generated by the antenna itself are easier to track, since they'll just go from the positive rod to the negative rod. But as the direction current switches, the direction of both the electric and magnetic fields change. To grasp the effect of changing fields in motion, let us model an electromagnetic wave as it travels through three-dimensional space. First, note the direction that the wave is traveling in the x direction. Now plot the electric field oscillating back and forth in the y direction. The electric and magnetic field always act perpendicular to one another. so the magnetic field will oscillate in the z direction. Note that the electric and magnetic fields both peak at the same time, so they are in phase. These electromagnetic waves are type of transverse wave, which means both fields, electric and magnetic, acts in directions that are perpendicular to the direction in which the wave is moving. And how fast do these waves travel? Maxwell's calculated the speed of each wave is equal to the electric field's magnitude divided by the magnetic field's magnitude. This equation simplifies down to an equation with two constants, the permittivity of free space for electric fields, epsilon naught, and the permittivity of free space for magnetic fields, and mu naught. And this speed works out to 3.00 times 10 to the power of 8 meters per second. We rewrite it simply as a small c, and it is the speed of electromagnetic wave, at least in a vacuum. You may know better as the speed of light. After all, light is an electromagnetic wave. Every electromagnetic wave carries energy through space and can reflect off some material while passing through others. But visible light is just one small part of what's known as the electromagnetic spectrum. Like waves in the ocean, electromagnetic waves can vary in their wavelength, amplitude, and source. The wavelength is the distance between the peaks of a wave, and the frequency is how many times a wave peaks in a given second. You might remember when we talked about traveling waves that a wave's speed is equal to its frequency times its wavelength. And since the speed of light is constant, you can easily find the frequency if you know the wavelength and vice versa. Now, in order to calculate the energy carried by an electromagnetic wave, you need to know the magnitude of the electric and magnetic fields that compose that wave. Specifically, you use these magnitudes to calculate what's known as the energy density of each field, which is the amount of energy stored in a field per unit volume. Then you combine the energy density for both fields, solving for the total energy per unit volume within the wave overall. So here's the calculation of the speed of light that Maxwell found. And the constants that is simplified down to. You can take our energy density equation and substitute the magnetic field magnitude, B, with the electric field, times the square root of the permittivity constants. With this simplified energy density equation, you can then substitute the electric magnitude for the speed of light and the magnetic field magnitude. One last important measurement of delivering energy is intensity, which is the energy transported by a wave per unit time per unit area. Mathematically, the energy delivered is equal to the energy density times the volume of space in which energy is transported over a period of time. You can then replace every density with one of the simplified equations we used earlier, so the volume of space encompassed by the wave is equal to the unit area times the distance traveled. And the distance traveled will be the speed of light multiplied by the time period. After canceling out like terms, you're left with an equation that tells you how much energy you have per unit area based on the strength of the electric field, which you can also replace with the magnetic field magnitude. But the vast knowledge of electromagnetism that we have today and the doors it has opened into the fields of relativity and quantum theory are all based on the theories that Maxwell and his predecessors developed. Albert Einstein praised Maxwell specifically for his contributions, but it was the combined effort of revolutionary minds like Maxwell, Faraday, Gauss. Albert Einstein praised Maxwell specifically for his contributions, but it was the combined effort of revolutionary minds like Maxwell, Faraday, and Gauss that we have to thank for our understanding of the interaction between electric and magnetic fields. Today we learned about Maxwell's equation and their unifying power in the field of electromagnetism. We discussed electromagnetic waves and how changing electric and magnetic fields propagate through space. And we investigated the different types of waves on the electromagnetic spectrum as well as how to calculate the amount of energy they can carry.